You felt the pull. Two pieces of iron, separated by space, suddenly leaping across the gap and slamming together. We intuitively credit this to classical magnetic fields interacting with each other. But the calculated dipole-dipole forces between atoms are vanishingly weak. They lack the strength to keep a solid piece of iron magnetized at room temperature, where thermal energy should instantly scramble the alignment. Left, classical physics treats magnets as interacting bar magnets. Right, quantum reality shows overlapping electron clouds, where spin alters the material's energy. Heisenberg realized the dominant force is electrostatic Coulomb repulsion. Crucially, this force ignores spin, evaluating only physical distance between particles. Magnetism arises as an electrostatic consequence of the Pauli exclusion principle. The forces we perceive as magnetic are actually the result of these quantum rules dictated by spin. Electrons are fermions, meaning their total wave function must be antisymmetric. If two particles swap places, the entire wave function sign must flip to negative. Physicists separate this total state into the product of two distinct components, the spatial part and the spin part. To keep the total state antisymmetric, the spatial and spin components must be absolute opposites of one another, as shown in this matrix. Parallel spins, the symmetric triplet state, mandate an antisymmetric spatial state. Conversely, opposite spins, the antisymmetric singlet state, force the spatial part to be symmetric. Spin alignment dictates the physical, spatial geometry of the electrons. While the spins do not generate force directly, their symmetry rules determine how the electrons distribute themselves in space. Spin controls electron cloud shapes. For parallel spins, a central physical node forces the electrons apart, suppressing Coulomb repulsion and lowering energy. Conversely, opposite spins lack this node. Their probability clouds merge, increasing electrostatic repulsion and driving up the system's energy. Parallel spins lower a system's energy because the Pauli exclusion principle physically separates the electrons, neutralizing their natural electrostatic repulsion. Calculating this exact energy difference requires shifting from visual intuition to mathematical rigor. The direct Coulomb integral, C sub AB, calculates the baseline electrostatic repulsion expected between two spread-out charge clouds. The exchange integral, K sub AB, introduces a different structure. Here, the orbital labels A and B are crossed between the bra and ket notation. This term represents a purely quantum mechanical amplitude for exchanging indistinguishable orbital assignments. No physical movement or trading of positions occurs. This equation shows the exact energy gap between the singlet and triplet states. The triplet energy minus the singlet energy equals approximately -2 times the exchange integral. With a positive K, the triplet state lies at a lower energy. This integral, K sub AB, is the microscopic root of the ferromagnetic tendency. It quantifies the energy saved by aligning spins between two interacting atoms. Moving from isolated atoms to a solid material requires accounting for a dense crystal lattice. To model spin interactions across these structures, physicists use the Heisenberg Hamiltonian and the exchange constant, J sub ij. J summarizes the final net magnetic coupling in a solid. Navigating academic literature requires checking the specific mathematical conventions used in the Hamiltonian. In convention A, a negative J favors parallel spins and ferromagnetism. Convention B inserts a negative sign into the base equation, meaning a positive J indicates ferromagnetism. The exchange constant serves as a contextual modeling parameter. Its interpretation depends entirely on the mathematical framework chosen by the author. Direct orbital overlap fails to explain magnetism in many insulating transition metal oxides, where magnetic ions are physically separated by other atoms. In these materials, magnetic ions interact indirectly through a non-magnetic oxygen bridge in a process called superexchange. Pauli exclusion blocks virtual hopping if the neighboring ion already holds a parallel spin. Only anti-parallel spins are permitted to virtually hop, resulting in an antiferromagnetic coupling. Philip W. Anderson formalized this mechanism, providing the foundation for understanding magnetic insulators. Ultimately, the exchange interaction explains how electron wave function symmetry generates the specific magnetic order observed in solid-state materials.